Thank you for introducing me, Larry, and a massive thank you for this opportunity to present here. So many good presentations today. So I'll be talking about this study, which was part of my PhD. So we tried to use a compositional approach to investigate the association between what we call movement behaviors, physical activity, sedentary time, and sleep, and what was the association with those movement behaviors with health outcomes in adults and children with cystic fibrosis. So we all know the benefits of physical activity, not only for the general population, but particularly for those with CF. So just to quote a few of those benefits, regular practice of physical activity can delay the lung decline, help with bone health, which will prevent osteoporosis, increase aerobic function, and help with nutritional status. All of this will ultimately lead to a better quality of life. But the problem is all the research out there showing the association between physical activity with those benefits is quite conflicting. We also don't know what intensity people with CF should be exercising or being active and for how long. So one hypothesis is that this previous research did not use compositional analysis. So we know that physical activity is compositional in nature. So if you look at the behaviors we have on a day, it's sleep, sedentary, light physical activity, and moderate to vigorous physical activity. They're all contained in 24 hours. So if I increase moderate to vigorous physical activity, for example, I'll have less time for the other behaviors. So one behavior will affect the other. And what compositional analysis does is that it normalizes this data, this relative data, which is the physical activity data. And so we can then use normal statistics analysis. So with this in mind, we wanted then to investigate the association between these movement behaviors with FEV1 predicted in children and adults with CF, and see if we get any more clear responses on this association. So to do that, we assessed 129 participants with CF, and among those we had 86 children with an average age of 13 years old and FEV1 predicted percent of 86, and 43 adults with an average age of 24 years and FEV1 predicted of 63%. So we measured their height and weight. We performed the spirometry of them, and we assessed their physical activity during 7 days using 2 accelerometers. So every one of our participants wore at least one in a non-dominant wrist. So we selected these models because they will allow us then to extract the raw data, which then we inputted in the R software, and then we used the GIR to be able to extract the time accumulated in sedentary, light, and moderate to vigorous physical activity. We also used the accelerometers to measure sleep time. So I'm going to run briefly through the compositional analysis. I'm going to be very brief. So if you want me to go into more details, I'm happy to do it after the presentation. So we can summarize the compositional analysis in 4 steps. So the first step is normalization. So here we have lots of different approaches to do this, but the approach we selected was the isometric log ratio transformations. So this approach will normalize the data and transform it in IRL coordinates, and then you can actually use those IRL coordinates to apply any other kinds of statistics on them. So then the next step was we applied then multiple linear regression on our coordinates and adjusted it for age, sex, and genotype. And we also included FEV1 in this regression. And then the other step then was sequential binary partitioning. So if you just look at the IRL coordinates, they are quite hard to interpret. It's really hard because they include all the 4 behaviors. So if you use the binary partition, that will break those behaviors in different, the composition is then broken in different parts, and you can then try to explore how those parts are associated with each other and how they will impact FEV1. So for example, I can have a numerator with sedentary and sleep as numerators, and as denominators, you would have MVPA and LPA. And then you play with increasing and reducing the different behaviors and seeing how this will affect the FEV1. So that was what we did on the last step then. We then reallocated from 10 to 30 minutes between each behavior. So for example, we would increase 10 minutes in MVPA and reduce with time displaced from sleep and see how that would affect our FEV1. We did that for all behaviors. So for all of our combination of behaviors. So here you have a description of our physical activity levels from our data, from our sample, and sleep. The first thing we can see here is that our girls were a bit less active than the boys. We also, in the adult population, females had more sedentary time than males, and they also had less sedentary time, and they also had a bit less LPA than males. So now I'm going to talk through about the results from the reallocations that describe that we changed from 10 to 30 minutes. I'm just going to present the reallocations we did for 30 minutes because of time. So the first result that struck us was that when we reduced 30 minutes of MVPA from time replacing time from LPA and sedentary, we had a reduction in FEV1. And we had the same result when we reduced time from sleep. We also had a reduction from FEV1. The only difference is when we reduced time from sleep from any behavior, we had this reduction. Similarly, we also had, when we increased 30 minutes of MVPA, we had an increase of predicted percentage changes. And I just want to highlight that this increases in the predicted percentage changes in FEV1. This only occurred when you're displacing this time from LPA and sedentary. If you displace the time from sleep, you would have the opposite change on FEV1. Sleep was the only behavior that increased. If you increase the sleep, it doesn't matter from which behavior you're displacing, you will have increasing FEV1. It's really demonstrated the importance of having good sleep habits. We also had any change actually in sedentary would cause increase in FEV1 from any behavior apart from sleep. So here you have an increase. The highest increase that we had was with the increase in the sleep, the highest increase in FEV1, which elicited an increase of 3.6%. It seems quite small if you look at it at first, but if you think the literature says that people with CF have a yearly decrease of 1 to 3% in their FEV1 annually, this is actually very significant because you can actually delay this decreasing lung function long term. Pardon me. So here, we have the ternary plots. That's how we display our data or relationships between each one of those behaviors. So first, here in this slide, you have the ternary plot for children, and the other figure is the ternary plot for adults. I'm not able to show you all the ternary plots we had, so I'm only showing you the association between sedentary sleep and MVPA. And what we have here is that when we increase sleep from MVPA or from sedentary, you then have an increase on FEV1. So the heat map is showing you the FEV1. So the areas in blue is where you have lower FEV1. The areas in red and yellow is where you have a bit of higher FEV1. And you have a similar thing in adults. The map for adults looks a bit different because even though I analyzed with 4 behaviors, you can only use 3 behaviors on the ternary maps because of the triangle shape. So here you have the time taken from sleep, even if it is for MVPA, will decrease massively our FEV1, especially in adults. So this was really important finding in adults. Then to conclude, I think our most important message from this paper is that how important it is then to increase MVPA, but not only thinking about MVPA, also thinking about the relationship with this behavior with the other behaviors. So only time displaced from light and sedentary increased MVPA. So yes, let's increase MVPA, but let's also keep a good sleep pattern for our patients with CF. And this will allow a greater benefit in the lung function. So, and the last thing I wanted to say is the important impact compositional analysis is having at the moment in this research field, not only for CF, but we're seeing a movement towards considering 24 hours a day. So for example, you have Australia with their guidelines on physical activity that is considering the whole 24 hours and all the behaviors in those 24 hours, including sleep. And then I believe compositional analysis will help us to even view physical activity in a different way. So for example, clinicians should be able then to look at all the behaviors instead of just saying, yeah, go do exercise on really moderate intensity. But maybe they also will look and understand the relationship between moderate intensity with the other behaviors, movement behaviors. I just wanted to say thank you to the CF Trust for funding this research and for all the co-authors that are still working on this paper to this day to get it published. And thank you everyone for listening.